Assalamu alaikum. Welcome to today's online lecture on principles of chemical engineering. In last lecture, we looked into the material balance procedure for reactive systems. Specifically, we looked into three methods. One is the method of atomic balance, the method of molecular balance, and we also looked into the method using extent of chemical reaction. And in the class before that, covered by Dr. Robin Christie, you were introduced on what is heat of reaction, how do you calculate the heat of reaction, and then what is standard heat of reaction, how do you calculate that using Hess's law. You were also introduced to the concepts of heat of formation and the heat of combustion. In today's class, what we will do is we will look into the general procedure of how to solve energy balance calculations for reactive systems. Now, there are two methods to do this. One is the heat of reaction method, and the other one is the heat of formation method. In today's lecture, we will look into the energy balance for reactive systems using the first method, which is the heat of reaction method. Our previous methods for solving energy balance equations is no longer valid for reactive systems. The issue with our technique in chapter 8 lies in regards to choosing the reference states. For non-reactive systems, we arbitrarily chose the reference state for each species in the problem. Now, this is simply not the case for reactive system. For example, look at this reactive system here. Here we have methane and oxygen, which is the inlet, and they are at 100 degrees Celsius and a pressure of 1 atmosphere. Now, methane is burnt here using oxygen, and the products of combustion, namely carbon dioxide and water vapor, now they are cooled to 250 degrees Celsius at 1 atmosphere. Now, using the old method in chapter 8, we would simply choose the species. Here in the inlet we have methane and oxygen. We would choose the reference points like 100 degrees Celsius and 1 atmosphere for convenience, because we see them in the problem statement. And for carbon dioxide and H2O, we would choose 250 degrees Celsius and 1 atmosphere. Now, in doing so, this would lead us to conclude that the enthalpy is zero, because we're choosing these values as the reference states. This is what we used to do in chapter 8. In doing so, the same procedure for reactive systems, this would now conclude to us that the enthalpy is zero, because we are choosing the reference states from the problem itself. Now, we know that there is an enthalpy change here and it is not zero. In order to solve this dilemma, we have two methods for energy balance for reactive systems. As I said before, one is the method of heat of reaction and the method of heat of formation. You will obtain the same answer to a reactive energy balance problem regardless which technique you choose. Therefore, your choice of method will often be dictated by mostly by convenience, much like your choice of atomic balance versus extent of chemical reaction method for the mass balance procedure. In fact, some of the same reasoning goes into both decisions for mass and energy balance. So, and both these methods, heat of reaction and heat of formation method, you will choose a different reference state, and you'll choose a different hypothetical process path. And when you solve a problem, you must indicate in your solution what your reference state is and which solution method you tend to use. And we mostly decide which method to go by the convenience and by knowing what data is given in the problem. So we will decide that, and when we solve more problems, we will become wise enough to choose each of the technique. Before we go into the heat of reaction method, let's do a quick recap of the heat of reaction. Now, heat of reaction is also called as the enthalpy of reaction. In simple terms, It is the energy that is released or absorbed when chemicals are transformed during a chemical reaction. If you look at the textbook definition, it says heat of reaction is the enthalpy change for a process in which stoichiometric quantities of reactants. Now, when I say stoichiometric quantities, these refer to the value corresponding to the balanced chemical equation. And these are at a certain temperature and pressure. And when these stoichiometric quantities of reactants, when they react at a specified temperature and pressure completely to form products, and when the products are either heated or cooled back to the same temperature and pressure, you will get a certain heat release, either heat release or heat absorption. This heat is called as the heat of reaction. Now, this is represented in terms of this symbol delta H, suffix R. And if you look at your book, instead of this cap, when you have this degree symbol, it is called as the standard heat of reaction, which is the heat of reaction at a specified reference temperature and pressure. And in this case, it is 25 degrees Celsius and 1 atmosphere. Now, the unit of heat of reaction is represented in kilojoules per mole. Let's try to see what it actually means. Now, let's take this reaction where 2 moles of A and 1 mole of B reacts to give 3 moles of C, and we see the heat of reaction at certain temperature and pressure is a negative 50 kilojoules per mole. Now, this negative value indicates that this is a exothermic reaction. That is, heat is released during this reaction, and if the number was positive, it means heat is absorbed. Now, if you look these statements here, it says that if 2 moles of A reacts, 50 kilojoules will be released due to the reaction. Similarly, when you can say that 1 mole of B reacts, 50 kilojoules will be released. Now, you can also look it from the product perspective. If 3 moles of C are generated, 50 kilojoules will be released due to the reaction. And if 1 mole of C were to be generated, then you will 50 over 3, which is approximately around approximately 17. So 17 kilojoules will be released due to reaction. In that context, we can also say that 1 mole of A, when reacted, will release 25 kilojoules per mole. Before we go into the heat of reaction method, let's review some important terms and definitions related to the heat of reaction. Now, the first thing I would like to highlight is that the value of heat of reaction depends on the stoichiometric equation and how this is written. For example, in this example, we have methane is burnt using oxygen. We have 1 mole of methane and 2 moles of oxygen. These are burnt and you get 1 mole of carbon dioxide and 2 moles of H2O. Now, this is an exothermic reaction where energy is released, and if you look at the heat of reaction that is measured experimentally, you see minus 890.3, that is 890.3 kilojoules per mole of heat is released. Now, imagine if you were to double the reactants, that is, if you were to use 2 moles of methane and 4 moles of oxygen, and if you were to look at the corresponding heat of reaction, you will see that the heat of reaction gets doubled. Now, the takeaway from this is that when you double the quantity of reactants, then the total enthalpy of the reactants and also the enthalpy of the products gets doubled as well. And the second observation is that at low and moderate pressures, the heat of reaction becomes independent of pressure, and at very low pressures, heat of reaction becomes only a function of temperature only. Here, let's talk about the heat of reaction, or the standard heat of reaction. This is the heat of reaction when both the reactants and the products are at a certain specified temperature, reference temperature, and in this case it is 25 degrees Celsius and 1 atmosphere. The standard heat of reaction is calculated by using the Hess's law. According to Hess's law, if a stoichiometric equation for a reaction can be obtained as a linear combination of the equation for other reactions, that is by adding and subtracting equations, then the heat of the first reaction can also be calculated as the same linear combination of the heats of the other reactions. This is what we call as the Hess's law. The next thing I would like to talk about is that the value of the heat of reaction depends on the physical state of the species, whether they are gas, liquid, or solid. For example, if you look methane combustion here, we have 1 mole of methane and that is burnt with oxygen, and you have carbon dioxide and water, which is in the liquid state, and this is at 25 degrees Celsius. When you burn methane and oxygen, usually the products of combustion are at 1400 to 1500 degrees Celsius, which is the maximum temperature. Imagine when you were to cool them down to 25 degrees Celsius, you would get minus 890.3 kilojoules per mole. Now in this case, the H2O is in liquid state, that is from the gaseous state it is cooled down. It goes through a phase change from gaseous to liquid. Now the same reaction where you burn methane, let's assume that the water vapor does not go through a phase change, but instead it is still in the gaseous state at the same 25 degrees Celsius. Now if you wonder why H2O is in the gaseous state at 25 degrees Celsius, it's because the pressure is not the same. It might be at very high pressure. So in this case, if you look at the heat of the reaction, it is minus 802. So the heat of reaction for the first case is high because there is a standard heat of there is a latent heat involved here when the water vapor becomes a liquid, which is not here. In the second reaction, the water vapor is still in gaseous state. It has not gone into liquid state, so the latent heat is not released. So what we're trying to say in here is that the heat of reaction depends on the physical state of the reactants and products, whether they are in liquid or gaseous state. Now let us look at an example. In this example, we have 2 moles of A react with 3 moles of B to give us 1.5 moles of C. The standard heat of reaction for this chemical reaction is negative 500 kilojoules per mole. You see the negative value because this is a exothermic reaction and heat is released. Now the question is, what is the standard heat of reaction for this equation? This equation is there is 1 mole of A reacting with 1.5 moles of B and gives you 1.5 moles of C. Now as per the Hess's law, if you can arrive at this equation from the first equation by doing any linear algebraic calculation, then you can perform the same linear algebraic calculation on the standard heat of reaction. That is, if you look at this second equation, this is almost equal to half of the first equation. So if you were to calculate the standard heat of reaction for the second equation, you can divide the standard heat of reaction of the first equation by half, so which is minus 250 kilojoules per mole. Similarly, let's look at the second problem. If 6000 moles of A is reacted, then what will be the amount of energy that will be released or consumed due to reaction only? Now the question is it released or consumed? Now here we know that when 2 moles of A react, 500 kilojoules per mole are released. So what happens when 6000 moles react? Now for every 2 moles that react, we have 500 kilojoules per second that is released, and for 6000 moles simply you have to multiply it. And when you multiply it, you get this very large number, which is basically the heat that is released. So the takeaway here is that you can perform any algebraic calculations, addition and subtraction or division on the reaction. Simultaneously, you can do the same for the heat of reaction. Now let us discuss certain important things before we look into the procedure of heat of reaction method. The first one is that this heat of reaction method is useful and ideal when there is only a single reaction in the problem, and for which you know the standard heat of reaction, or you can calculate the standard heat of reaction from the Hess's law. The information should be available in the problem. The second thing is that this method requires that you know what is the extent of chemical reaction. Uh, in the last lecture, we discussed the material balance for reactive systems using the extent of chemical reaction. That is this symbol Z. Now you must know the value for extent of chemical reaction on either a reactant or a product, and you must know the feed and the product flow rates for any one reactant or product. So when you know the extent of chemical reaction, then you can use this technique, which is the heat of reaction method. And you also note that the reference state for the reactants and the product species are 25 degrees Celsius as temperature and 1 atmosphere pressure. Now in the problems, you will also encounter certain species which will not react. For example, nitrogen. Now for these species, you can have the reference state as stated in the problem. You can use the inlet conditions, inlet temperature pressure or outlet temperature and pressure as the reference conditions, what we used to do for non-reactive processes in chapter 8. For example, if you have nitrogen, you can use 25 degrees Celsius and 1 atmosphere. This is because the tabulated data in table B8, which is given at the back of the book, these data for nitrogen are given at 25 degrees Celsius and 1 atmosphere. So if you choose this as the reference, then you can easily calculate the enthalpy for these for nitrogen at any temperature and pressure from the table. In this slide, let us discuss the general process for heat of reaction method. So as soon as you read the problem, the first thing you do is you will draw the flow sheet, and you will name the streams, the input and the output streams, and you enter all the information on the streams, like the species involved, the flow rates and their corresponding temperature and pressure. Also please write what is the state of the species, whether they are gaseous state, liquid or solid. Now the first step before you do energy balance is that you must do the material balance calculations. Now you must carefully look into the problem statement, and if some of the values are missing, if some of the flow rates are missing, then you must use material balance methods like either the extent of reaction. Use this method to calculate the all the flow rates of the inputs and the output streams. The second step is you must choose a specific reference state. In the heat of reaction method, the references are the reactant and product species at 25 degrees Celsius and 1 atmosphere, for which the heat of reaction is known. And in the third step, you will calculate the extent of reactions. Choose any species. It can either be the reactant or the product for which the feed and the product flow rates are known. Now, after you do this, we prepare the enthalpy table where you list all the species, and then you calculate the inlet and the outlet enthalpies. And the next step is that we will calculate the change in the enthalpy for the entire reactor. Now we will do all of this for a specific problem, and if the problem has a single reaction. Now remember, the heat of reaction method is ideal for single reactions, and if you have multiple reactions, I would suggest you use the heat of formation method that will be taught in the future classes. And after you calculate the change in enthalpy, you can perform the energy balance and complete the required calculations. So this is the general overall procedure. We can see all of these procedures in an example in the coming slides. Let's try to explain the heat of reaction method using the propane combustion. Here we have propane that is burnt inside a furnace. Now propane here is at gaseous state at 25 degrees Celsius, and 100 moles per second is the inlet flow rate that goes into the furnace. The propane here is burnt along with air. Air now here combines oxygen and nitrogen in the bulk. The oxygen flow rate is 600 moles per second, and oxygen here is in gaseous state, and we have nitrogen which is at 2256 moles per second. Now the air or the combination of oxygen and nitrogen are at 300 degrees Celsius. Now one thing to remember is that nitrogen here is will not react because we send air. Nitrogen is part of air, and this will just come out. But this nitrogen, of course, will get heated, but this will not take part in the chemical reaction. Now, if you look at the exit streams, we have oxygen. This is the unburnt. This is the oxygen, that is the excess oxygen, and then we have nitrogen. You can clearly see that all of the input nitrogen has come out. All of the 2256 moles per second of flow rate is there, so all of the nitrogen comes out. Then you have carbon dioxide and H2O, which is because combustion of hydrocarbons will give you CO2 and H2O. The flow rate is also given, and the entire products are at 1000 degrees Celsius. Now this reaction, which explains the propane combustion, we have 1 mole of propane, 5 moles of oxygen give you 3 moles of carbon dioxide, and 4 moles of H2O. The standard heat of reaction for this problem is given here. It's minus 2220 kilojoules per mole. In this particular problem, we don't have to do any material balance calculations because the numbers have already been provided. So all we need to do is we need to do the energy balance, and we will do it using the heat of reaction method. There is no need to perform material balance calculations because the flow rates of the input and the output streams are specified in the problem itself. The second step would be to choose the reference state for calculating the specific enthalpies. The best choices are generally reactant and product species at 25 degrees Celsius and 1 atmosphere in the states for which the heat of reaction is known. And in the present problem, we choose 25 degrees Celsius and 1 atmosphere for all the reacting species. We also choose the same reference state for nitrogen, which is not reacting here. If you refer the table B8 in your appendix of the book, you will find a table for nitrogen, which also has a reference at 25 degrees Celsius and 1 atmosphere. So when we choose this reference state, we can easily calculate the enthalpy. So that's why we are using the same values for nitrogen as well. The next step is we need to calculate the extent of chemical reaction. The first step in this thing is we must choose one species to calculate the extent of chemical reaction. Now you must know what is the input and the output flow rates for this species, the species that you choose. In the present problem, since we have the values for all of the species, it doesn't matter which one you choose. So presently we have chosen propane. So if you look at the formula to calculate the Z, which is the extent of chemical reaction, it is the output flow rate minus the input flow rate divided by the stoichiometric number that you take from the balanced equation. So there is no propane that is leaving the reactor because all of it is getting burnt, and 100 moles per second is entering the reactor, and the stoichiometric number corresponding from the chemical equation is 1. So your extent of chemical reaction is 100 mole per second. Now, please do not use nitrogen as the species because nitrogen is not taking part in the reaction. If you take nitrogen as the species, you will get the value as 0. The next step is for us to prepare an inlet outlet table where we list out the all the species. So we first write the substance and we write all the species encountered in the problem, and then we write the inlet and the outlet table. And in the inlet we must know the flow rates of each species and also the corresponding specific enthalpies. And similarly we do the same for the outlet. Now, when we for any species which is at the reference state, we will write the value as 0. Now, in this problem, since the reference state is at 25 degrees Celsius and 1 atmosphere, and propane is entering at the same this reference state, so we give a corresponding inlet in specific enthalpy inlet is 0, and then we need to enter the other values from the flow sheet. For those specific enthalpies which we do not know, let's try to give them certain numbers, H1, H2, H3, H4, H5, and H6, and we need to calculate these values to complete the table. Now we need to calculate the specific enthalpies for the input and the output streams. In the present case, calculating these values is easy because uh, the species we encounter in the present problem, namely oxygen, nitrogen, carbon dioxide, and H2O, the specific enthalpies of all of these species at different temperatures is available in the standard table, table B8 in your appendix. So, for example, in this particular problem, nitrogen is at 1000 degrees Celsius in the output stream. Now we can easily go to the table B8 and we can calculate what is the specific enthalpy at 1000 degrees Celsius. And since the reference is already at 25 degrees Celsius, we can directly take the value. Similarly, we can take all the values for the input and the output stream from the enthalpy table. The only trick here would be to calculate the specific enthalpy for water vapor H2O at 1000 degrees Celsius. The reason is that the other species that we encountered here, namely oxygen, nitrogen, carbon dioxide, all of these are in the gaseous state, and none of these species undergo a phase change. But here we need to calculate the specifically H6 is the specific enthalpy for water vapor at 1000 degrees Celsius. Now we have the value for water vapor at 1000 degrees Celsius, but we also need to calculate, or we need to consider what is the latent heat involved here, because we are going from 25 degrees Celsius to 1000 degrees Celsius. So from the table, we know what is the value at 25 degrees Celsius for water vapor, which is 0. And for 100 degrees Celsius, it is approximately uh, 2.54. And then we need to calculate what is the value for latent heat. So we can take the latent heat values from the table B1 from the appendix, because there is a latent heat here. And then from 100 degrees Celsius to 1000 degrees Celsius, we know what is the corresponding change in the enthalpy. So the enthalpy for this H6 for water at 1000 degrees Celsius, you need to consider the latent heat because there is a phase change. Now in the last step, we calculate the change in the enthalpy for the entire reactor. We have the formula here. This Xi is the extent of the chemical reaction, which we calculated before using propane as our species of interest, and we calculated the value to be 100 mole per second. We can also use other species in the reaction, provided we know the inlet and the outlet flow rate. So you will also get the same value if you use other species as well. Then we have we multiply this extent of reaction with the standard heat of reaction, which is minus 2220 kilojoules per mole. This value is provided in the problem. Then we have the summation term here. We multiply the output molar flow rate with their corresponding specific enthalpies, and then we have the summation term here, which is the product of the feed flow rate corresponding multiplied with it corresponding specific enthalpies. So when we do a summation, we get the change in enthalpy for the reactor to be minus 1.26 into 10 to the power of 5 kilowatts. And this concludes our heat of reaction method, where we do the energy balance for reactive systems. And in the last step here, we apply the first law of thermodynamics. We calculate the heat transferred, or the heat taken out from the reactor, and we calculate the final value. So we here in this lecture we explained the heat of reaction method, and in the coming the next lecture we will solve two or three more problems, so that we are able to understand this heat of reaction method. And after that we will look into the heat of formation method. We will do energy balance for reactive systems using the heat of formation method. Thank you.